Greetings, Earthlings! Today we're going to take a look at adding some non-volatile storage to the OOD11 computer. Now, if we were staying strictly, historical or vintage, we'd look at floppy disks or hard drives or deck tape. But those things are, because, the adapter cards are available for them, but the drives themselves are getting old, they're mechanical, they're prone to failure just due to age, and probably very difficult to repair. So I'm looking at a different solution. And my solution involves, I should state my requirements up front as much as possible. I don't need a whole lot of storage. So we're looking at here a 0.5 megabyte, which is sufficient. And that's about what a floppy disk would hold. I don't need super speed, and but I do want interchangeability. So we'll look at that. Okay. So I'm bring this. What I have is what I'm going to use is right there. These are 512K by 8 parallel flash memory. Now, how do we get the computer to access that? Well, we could do a custom board, full custom board. That gets difficult because some of the driver chips that DEC used for the Q-bus are really not available. So you have to use substitutions, things like that. And that would be sort of a lot of work. So what I've got is, this is an M7651, also known as a DRV11WA. It's a parallel interface. This card is actually capable of doing direct memory access, or DMA. I'm not going to be taking advantage of that, at least in this first iteration. So we're just using it as a parallel port. Okay, and you see it has these connectors, and so it does require a custom board. And the custom board, here we go. Now I got this as a completely blank board from Douglas Electronics. You see, beep. Douglas Electronics 9DE11. You can look them up on the web. They make, I know. I'm going to turn that off. They make a number of different adapter cards, Q-bus cards, and for various other things, prototyping cards and so on. And you can see the circuit there, and you can see I have a ZIF socket for the flash memory there. And then it'll connect via these ribbon cables to that other card. Okay. Looking at the schematic, it's not all that complicated. What I've done is divided my 0.5 megabyte, 512K bytes, up into 64 8K byte pages, because that is what suits me. And so I have a register here, which, this is the register. This holds the page, so 6 bits of page. And then there will be 13 bits of address coming in. There's a 8-bit buffer here for holding the write data, if I want to write to the chip. And then this chip down here at the bottom decodes some bus signals to tell me what operation I'm doing. And this just provides the appropriate timing on the writes to the chip. I'm using some 74LS31 delay lines there to provide the timing. Okay, so out here you can see this is the bus. These are the interface signals from those blue connectors. 16-bit. This is a 16-bit machine, right? And it's a 16-bit bus. I'm only using 8 bits. Obviously, I could make this a 16-bit wide thing, and I could add, DMA and all kinds of stuff. But again, this will suit my needs. And then there's a control and status register. So there's one sort of register on that card that holds the output data and input data. Okay, so when we're reading, we come here, and that'll show up in that data buffer. And then there's a control and status register, which has these function bits. Okay, and there are 3 function bits. So I'm actually only doing 4 operations right now. We can read, we can set the page register, we can set the data register, or we can do a write. So reading just involves setting the page register first, okay? But that's something you're going to do once if you stay within a page. You set the page register. Then you're going to set into the data register the address within that page, 13-bit address, and then you can just read the data out of the data register, and that's a read. So, and then to read the next byte, you increment the value that's in the data buffer, store it in there, and then you can immediately read. So reads are fairly simple and fairly fast. A write is more complicated because for a write, we've got to first, well, of course, we'll set the page register somewhere in here, but for a write, we've got to set the data into the data register. Then, okay, set the page register, put the address on here, and then we say write. Then, of course, because of the way these chips are, we have to wait for that write to complete, but that's just doing a bunch of reads. So the write is, as you see, more operations because we have to save that data because we only have the single input bus here to the device. We have to save that write data into a buffer because when we are performing the write, what's on that bus is the address. Okay, that's what the timing looks like. A, B, and C here are just my internal things, but we have a write signal coming in from the bus. So there's an output enable on the flash memory. There's an output enable on the buffer, data buffer chip, and then there's the write enable on the flash memory. We don't want overlap on the output enables because then you get bus contention and it's hard on the chips. And then there's certain setup and hold times that we have to meet, and so that's what that's all about. So let's see. So these plug together. This is J1, J2, and I have these labeled. This is J2, so that's going to go in there. And I should have done J1 first, as you can see, because now I can't see what I'm doing, and you can't either. Okay, here's J1. I said, here's J1. There we go. There's J1. And now we can plug this card into the bus. Okay, yeah. Let me plug it in. Let me plug it in here. Okay. And now this other card also plugs into the bus. It's only getting the power off of the bus. So all the control signals and everything come through these ribbon cables. But it is pulling power off the bus. I could have used a different card. There's actually a connector on here, a 2-pin connector that has power and ground on it. And I could have used a smaller card that didn't plug into the bus. But this is convenient because it keeps everything together. Now this can plug into any bus slot. And bus slots, oh well, that's an interesting concept on the Q bus. There are two kinds of bus slots. There are the ABs, which is what your regular cards plug into. And then there are the CDs, which is, well, some cards are for quad width. These are dual width. But the CD bus is just used. So AB is the Q bus, and CD has a sort of little private bus. The first three slots on this card are CD slots. These are all AB on this side. First three here are CD, and then these are AB. So you could put, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 more of these dual width cards onto this bus. This is an H9278A, by the way, for those keeping score. But this can plug into either an AB or a CD because the power and the ground are on the same pins on both, and I'm not using any other data lines or anything. Okay, so what I've done, now I can turn this back on, and I can turn this on, and what I have done is I have actually burned into the first page hello world text. So I'm going to need my cheat sheet here. So the control register is at 772414, and the data register is at 772416. Okay, so I'm going to go 772416 and set that to 0. First thing we're going to do here is set the page register to 0. It's probably 0 already, but that's okay. 772414. I put a 2 in there. That brings the clock line for the that latch that holds the page register data. That asserts that, and then I'll turn it off, 772414, put it back to 0. Okay. And now if I go 772416, yeah, okay, I'm going to put 0 in there again. It's still 0, but, we'll go through this as if we didn't know that. 772416. Now reading that data register will give me the value in location 0. And it is 110 octal. 110 octal, 110 octal, which is an H. How about that? Okay. So if I now, 772416, let me put a 1 in there. Okay, now 772416, reading that location gives a 105, which is an E, and so on. So you can see I'm able to read that chip. In terms of writing it, that's, like I said, a little more complicated and made even more so by the chip itself, which requires a certain sequence of operations before you can actually write the data. So I wrote this program and hand assembled it and ran it before I started this video. And what this does is this writes a 0 into location 0 of page 1. Here's my set page register to 1. What I did at the beginning is I set register 4 to point to the control and status register, and register 5 to point to the data buffer register. So I'm just doing indirect addressing throughout this to those two registers. It's pretty simple. And then waiting for completion is okay. So if I set the page register to 1, because I'm not gonna toggle that program back. And besides, it's already set. I'd have to go and erase it, and that's hard. So I'm gonna set the page register to 1, and we put a 2 in there, and then we put a 0 in there, and then we go 2, 4, 1, 6. I'm going to put that back to 0, and we're going to read it, and you can see now that that's obviously we're accessing different memory here, because this first read, because anytime we access the data, we're reading the current, whatever the address that's currently specified, that address's data is presented on the bus. So we read that. It's the 377, which is an FF, which is an unprogrammed cell, and that was at location 1, because that was the last thing we put into that data buffer register. Well, when I set it back to 0, now we're reading location 0, and you can see that that is indeed 0. So when I read page 0 up here, I hope that's on the screen. I read page 0. I got the hello world. When I set the page to 1, you can see I got the 0, which I wrote using the OOD11, using this circuit, and not on the PROM programmer, which is how I put hello world in there. Oh, there's one thing I didn't show, and that's this button. Well, this button on the back here is just connected to one of the lines on the control and status register. It has three status lines: status A, status B, status C. So that just comes in as status A. By the way, see, there's funct1, funct2, funct3, which were those control lines, and the in and the out lines, and none of the rest is being used at this point. So that's what that button's for. That's can be a little attention signal. If you have your program checking that bit to see if the button is pressed. So that's it for now. We've got some non-volatile storage that the OOD can use, a whole half a megabyte, which is a lot back in the day. Well, again, not really a lot. It's about a floppy disk's worth. But I have replaceable drives. There. That's $2, and pop in a different disk. Well, chip. And I'm not going to be trying to boot off of this, and I'm not going to be running, an operating system, RT11 or anything. My plan is, recall that the multifunction board has EEPROM sockets on it. So my plan is to put the code that I need to run, that I want to run, into EEPROM, and then we'll just have this as external non-volatile storage. It'll all make sense eventually, I'm sure.